Okay, so now let's see how many kids come. I know, but
and is that for YouTube?
Okay. Are there no questions? This is for grade 11, Nathan. If the grade 12s have questions about their lab, I'll answer them as well. This is so I'm here to answer questions for grade 11s for their test tomorrow. But if grade 12s have their question about their lab, I can answer that as well. Okay, for NH4, what do you want? The Lewis structure. So you would have to write the intermolecular forces or potentially show them. Do both, depending on what I ask you. So if I ask you, so if I gave you that molecule and I asked you for what intermolecular forces it would form, you would have to do the Lewis structure. And then from there, then you would look at the AXE. So we know that this would be an AX4. Okay, our oxygen we know has lone pairs on it. So that would be an AX2E2. Is the video showing straight for you? Because for me, it shows flipped. If I were... So is this good? Does this show good for you? Because it's flipped for me. So if we looked at our NH4 plus, like somebody asked before, we would see that in our NH4 plus, right? It's a charged ion, so it's going to go in square brackets. It has an AX4 structure. So if we do our Vesper diagram, and for the grade 11s, you'll have this on your test. Okay, now this is we know that the nitrogen to hydrogen bond, we would look up its electronegativities and we would see that it is greater than 0.5, so it's a polar bond. So we would have our poles. However, because it's a symmetrical molecule, the polar bonds would cancel out. And so there would be no net polarity for this molecule. Okay, and so therefore, I'd say is London forces, but because this is a charged ion, we're going to have electrostatic attractions. Okay, now because these hydrogens are bonded to nitrogen, if we had this with water, even though this is a non-polar molecule, these hydrogens could be attracted to this oxygen, and so therefore we would get our hydrogen bond, right? Now, because there's no lone pair in this nitrogen, we couldn't get the reciprocal hydrogen bond, so therefore this would be a one-way hydrogen bond attraction. Yeah, they can cancel out even if they point inwards. That's right. For a dipole-dipole attraction to occur, both molecules have to be polar. Okay, and our classic example where we see this is when we look at the soluble. We look at carbon dioxide when it's in water. Carbon dioxide is a non-polar molecule, but because it has oxygens with lone pairs, we can get a one-way hydrogen bond forming between it. So between my carbon dioxide and my water, I have London force and one-way hydrogen bond. So as a result, this carbon dioxide molecule doesn't have really high solubility. Yeah, symmetrical molecules are non-polar. Doesn't matter whether the polar bonds pull out or go out to Earth. For a molecule to be able to form a hydrogen bond attraction with another molecule, we do need a lone pair. For both grade 11s and grade 12s, being able to decipher whether a molecule is polar or not from its shape is important. Grade 11, you will get the Vesper shapes, right? So the ones that we have in grade 11 are linear, right? And so carbon dioxide fits into that, and it has an AX2 format. We have trigonal planar. That's our AX3. We have our tetrahedral. AX4. Then we have our trigonal pyramidal. It's our AX3E, because there's a lone pair on a central atom there. And we have our bent. A good bet is if a molecule has lone pair, the polar bonds won't cancel out. So if there's a polar bond in a molecule with a lone pair, it is going to be a polar molecule. For high solubility, we have to form equivalent or greater attractions with ourselves in the molecule that we're forming it with. Okay, so this is why so if I have, for example, and I'll go back to my carbon dioxide again, right? The only attractions that carbon dioxide forms with itself, because it's a non-polar molecule, are London dispersion forces. So we would expect, therefore, for this to have low solubility because it forms London dispersion forces with itself, and water forms London dispersion forces, dipole-dipole, and hydrogen bonding with itself. So we would expect there to be very low solubility, or none even. But because we get a greater attraction between these two than this has for itself, we get, I'd say, moderate solubility. And it's significant attractions between my solvent as well, the thing that is being dissolved in. Because if I look here, right, we have our London forces. And then we have, because of our lone pair, we have our one-way hydrogen bond. So the attraction between these two are greater than the attraction that this has for itself. So I'd say that would be moderate solubility. I wouldn't call that high solubility. Conversely, if we look at, say, ammonia, which is a polar molecule. Okay, so as a result, it's going to form dipole-dipole attractions. Of course, we have our London force, and also we're going to have a hydrogen bond, and we can have our hydrogen bonding two-way. So this would be a high solubility. So I'm not going to ask you to decipher between low, high, or moderate. Basically, it's going to be soluble versus insoluble. Okay, so is this soluble? And I'll ask you, or I might ask you to rank two things. And so let's say I asked you to rank molecule A and molecule B. And we know that molecule A can form London force and dipole-dipole, and molecule B can only form London force. If I'm looking at a polar solvent, then I would say molecule A is, because it can form more attraction, it can form equivalent attractions with our solvent as it can with itself. Molecule B would low solubility because the solvent is more attracted to itself. If I'm looking at a non-polar solvent, right, an example that we kept using was cyclohexane, then I would say that molecule B would be more soluble than molecule A. And the reason molecule B is equivalent attractions, because it's non-polar, they'll both form London forces with each other. Molecule A would be more attracted to itself than to the solvent. So I'd expect less of this to dissolve than molecule B. So I'm not going to ask you to tell me the difference between moderate or high. It's more of these things, which ones would we expect them to dissolve more? Or it was noticed that these were more soluble. Yes, Tadessa, you're right. For two-way hydrogen bonding to occur, both molecules have to have a hydrogen bonded to a nitrogen, oxygen, or fluorine. One way occurs when one of the molecules has nitrogen, oxygen, or fluorine with a hydrogen. Okay. it's not so much identify the conductivity of compounds, it's what types of compounds would form an electrolyte and which ones wouldn't, right? So when we were talking about the conductivity test, that was like what we did when we were doing the stations on last week, right? And when I did the test where I took the device and we had the beaker and I stuck the 2-prong thing in with the bulb on top, and whether it gave off a light or not. And if it gave off a light, that means that there are ions in the solution that can ferry the electrons from one electrode to another. And so we, for that, we say that it's conductive. And only certain types of compounds allow for this, right? We know that ionic compounds will allow for this because when they form solutions, they release ions. And as I told you last day, acids and bases can also do this. Okay. Okay, so there's a couple of nomenclature questions. So first off, ortho and meta. This is because we have to use these prefixes because, as we said, we have our big 5 that we can use to determine the formula for a wide variety of polyatomic ions. And because both nitrogen and phosphorus are in the same group, I have to have to be able to distinguish which ones they follow. And so that's why we have our prefixes. We have the prefix meta if I follow nitrogen, and the prefix ortho if I follow phosphorus. And remember, we talked about the way in which we would determine which one it is by looking at the charge. So if I have this polyatomic ion, because the number of oxygens could change, I have to look at the charge. Because this has a charge of -1, that tells me that it's patterned after nitrate. And so as a result, I'd call this a meta. Whereas the same compound with a minus, a 3-, that would tell me that it's patterned after phosphate. And that would tell me that it gets the prefix ortho. So I have to look at the charge, and it only involves things that are in the same group as nitrogen and phosphorus. Okay, so arsenic, and then over on the periodic table in group 5. And so if I was doing this one, because it follows the nitrate or nitrogen, I'd call that meta arsen, because 3 oxygens goes with 8, arsenate. And if I was naming this one, because it follows phosphorus, I'd call it an ortho. And then because it's 3 instead of 4, it'd just be an arsenite. So the meta or ortho tells me if it's patterned after nitrogen or phosphorus. Okay. Now, the other question I have here is, what's the difference between hydrogen sulfate and sulfuric acid? Okay. Because my sulfate has a charge of 2-, that means it can pick up 2 protons to become neutral. So I could pick up 2 H+. Because then I have 2 positive, 2 negative, it'd be neutral. If I pick up a complete set of hydrogen, and I pick up 2 of them, and I'm now a neutral compound, then I'm a sulfuric acid. However, if I only pick up 1 of them, I have 2 minus, I have a 1 plus. I still have a minus charge, but I've picked up 1 proton. So this is still a polyatomic ion. So therefore, it's called hydrogen sulfate. Whereas this is not an ion anymore, we know, because it has no charge. It's picked up 2 H pluses to go with the minus 2 charge on the solid. And so that's an acid. So acids have no charges. Hydrogen sulfate has a charge because I didn't pick up enough hydrogens to neutralize it. Okay. Now, the net polarity of N2, because it is all by itself, what's my delta En? Well, this has an electronegativity of 3. This has electronegativity of 3. So the delta En is 0. So therefore, it'd be nonpolar. So there would be no net polarity on this. Some of it does dissolve in water, though, because it has a lone pair. But a N2 molecule is nonpolar. Sorry for my crappy camera, but it's probably older than some of you. No, they don't have to have a lone pair. They will dissolve in water as long as they are polar overall. So, for example, trying to think of one that's polar that doesn't have a lone pair. Oh, I know. No, that has lone pairs on it. So this molecule, because it's symmetrical, even though it's filled with polar bonds, it's nonpolar. Okay, so we would not expect it to dissolve significantly, except that we have fluorines with a bunch of lone pairs. So I would get London forces and one-way hydrogen bond. So this could dissolve even though it's a nonpolar molecule. Okay, so the lone pairs allow it to dissolve. Whereas if I looked at, say, this molecule, it has a positive charge. Okay, if I were to do the Lewis structure, or sorry, Vesper diagram, okay, so this molecule has no lone pairs on it, but it does have a series of polar bonds, and these are of different magnitudes. This has a electronegativity difference between nitrogen and hydrogen is 0.9. Difference between nitrogen and carbon is 0.5. Since they're of different magnitudes, they don't cancel out. So I have a net polarity. It might go something like this, maybe. And so because this molecule has a slightly negative and a slightly positive end, it'll dissolve in a polar solvent. Okay, and that so if I wanted to now dissolve it in, say, My solvent here, fluoromethane, this is a polar solvent as well. This is a polar molecule as well. So this will dissolve into that because they're both polar. So to determine if a molecule, if I have more than one central atom, I have to look at my Lewis structure. So here I could tell I had 2 central atoms because I have 2 atoms with more than one thing bonded to it. Whereas in this molecule, I only had 1 central atom because I only have 1 atom with more than one thing bonded to it. So that's my key, is do I have more than one thing bonded to me? If I have more than one thing bonded to me, I'm a central atom. Yes, Turt, that's correct. For something to dissolve in something else, it is based entirely on the intermolecular forces that form between those 2 compounds. If there are no significant attractions between those 2 compounds, they don't dissolve. If there are, then one will dissolve into the other. Whether the solvent be water, cyclohexane, or some other molecule. Yes, we do, depending on the oxy ion that's present, right? So if I had, for example, if I had H3PO5, I know that this polyatomic ion here is per phosphate. And so because it's an 8, the ending changed to ic acid. So this would be per phosphoric acid. Yes, ite becomes us acids. For grade 11, we're going to say that phosphorus will have 8 if it's not expanded, and if it's expanded, it can have 10. Sulfur, if it's not expanded, will be 8. If it has to be expanded, it has to be 12. Okay, and so in grade 11, we'll deal with that. You are correct that sulfur, when it's expanded, it can have 8, it can have 10, or it can have 12. But this year, you don't have to deal with the 10. Okay, so Tana, you asked a good question. If I have wish I could pay attention when I'm drawing things. So if I have this as my molecule, and let's say this is my solvent. So rather than dissolving something in water, I want to dissolve it into this. The types of attractions it can form will depend on what it's being attracted to. So if I have this molecule, which is a methanol. So now I'm looking at methanol with right. This is a polar molecule as well. So now the question is, what kind of attractions will form between these two molecules? Well, since they're both polar, we're going to get our London forces like we would expect. So we have our London dispersion forces, just like we would. And then because they're polar, the slightly negative end of this molecule will be attracted to the slightly positive end of that molecule. Even though both of these molecules contain oxygen and one contains fluorine, and there are other hydrogens in a molecule, since neither of them have a hydrogen bonded to either the oxygen or the fluorine, we would have no hydrogen bonds, attractions forming between these two. But if I have my other molecule that I was looking at before, so here, this is a aminomethane. Now what can happen is so this is a polar molecule with a net polarity. Okay, so again, I'm going to get, between my solvent and this, I'm going to get my London dispersion forces, just because they're between everything. I'm going to get an attraction between the slightly negative and the slightly positive end of the two molecules. Right, that's my dipole-dipole. And now here I have a hydrogen bonded to a nitrogen. So this hydrogen can be attracted to the lone pairs on these fluorines. And so I could get a one-way hydrogen bond. I wouldn't get a two-way because this molecule cannot form the reciprocal hydrogen bond attraction. Okay. So for a molecule to receive hydrogen bonding, it has to have a lone pair. For a molecule to form, it has to have a hydrogen bonded to a nitrogen, oxygen, or fluorine. Okay. Now, as to your question as to how do you know the Lewis structure for a big molecule, my camera, sorry, my camera is not behaving. So for a big molecule, for example, if I give you CH3COOH, what you can do is we know that the way that it's written tells us how it's going to go. So I have two carbons, and because in organic compounds, they're bonded together. And then on the first carbon, because it's a CH3, that tells me that that carbon has 3 hydrogens bonded to it. And a carbon needs four bonds. And then my second carbon has 2 oxygens, and the OH, because the H, because it's written like that, tells me one of the hydrogen is bonded to the oxygen. And because oxygen needs 2 bonds and carbon needs 4, we know that they have a double bond to each other. So the way that they're written tells us something about how they go together. Okay. That's right. They don't need to be connected to a hydrogen. So if we go back to this example, this fluorine is not, seriously, camera. This fluorine is not bonded to a hydrogen, but because it has lone pairs, it can receive a hydrogen bond. So to receive, we don't have to be bonded. All we need is lone pairs. So because it has lone pairs, we can get a hydrogen bond attraction formed to it. Because it doesn't have a hydrogen, it cannot form. Okay, so that's why we call it a one-way. It As lone pairs it can receive, no hydrogen cannot form. So yeah, so if you have big molecules, you'll get their structure, or it'll be written in a way that you can know its structure. If I have 3 atoms, right? So I have 3 atoms. One has a negative charge. One is neutral. And one has a positive charge. If they all have the same number of electrons, they're isoelectric, then the positive ion would be the smallest. The neutral would be in the middle, and the negative ion would be the largest. So if we talk about an example, so if I look at calcium ion, calcium would be my smallest. A chloride ion would be my largest, and then the argon that's in between them would be neutral. The more positive I am, the smaller I am. So therefore, if I had, say, potassium in here as well, potassium would be larger than calcium. And if I had my phosphide, it would be larger than chlorine. Yes, so so it comes down to 2 things, right? These are the largest because they have the smallest ENC. Their ENC value does not change when they gain electrons, and they have increased repulsion. This one, there's no change. Whereas these, remember, their ENC increases. And so that results in an increased force of attraction. That's why my calcium ions are smallest. Okay, and we can see that because if I look at my calcium ion, it has 20 protons. It has 2 electrons in its first orbital. It has 8 electrons in its second energy level. 8 in its third energy level. And 2 in its outermost. So when it's in this case, when I'm a neutral atom in this case, I have 2 plus 8 plus 8. So that means that I have 18 core electrons. I have 20 protons. This is why I have an ENC value of 2. But when I become a calcium ion, I lose these 2 electrons. So my outermost energy level is no longer there. This becomes valence. So now as a result, I only have my first energy level, and my second energy level is core. My third energy level that was core is now valence. So as a result, I now only have 10 core electrons. I still have 20 protons. So as a result, my ENC is no longer 2. My ENC is now 10. So since my ENC went up, then that means that I'm going to have an increased force of attraction. So I will say this. If you're asking about isotopes, do they fit between your fingers and your notes? The only thing we talked about with isotopes is their definition. So that's the only thing that you would need to know about them on the test. And I'm going to leave it at that, Sahegi. Yes, you will get the whole class for the test. How would you know if an element has a higher or lower melting point? Same as if we know for a compound that just has London forces. All you have to do is look at the total number of protons and electrons. No, you should not study them. The voice was alluding to maybe you saw an old version of the test, which your test no longer looks like because we didn't do isotopes. And in previous years, we did isotopes in the first unit. We moved them to, we're going to do them later in the year. So that's what the weird voice was about. The possibility that you maybe saw an old version of the test. Well, I can't really control my voice because I have a crappy mic. So if I wanted to look at a molecule, let's say ethane, and I wanted to compare it with undecane, because this molecule is larger, and I know it's larger because it has more carbons and it has more hydrogens, right? So it's going to be larger. So what this tells me is that I have more protons and I have more electrons. And since my London dispersion forces are due to the attraction of electron clouds and the shifting of electron clouds, since this molecule has more electrons in a bigger electron cloud and more protons, it will have a greater London force. Since its London force is higher, it'll have a higher melting point or boiling point. The format of the test is going to be multiple choice and short answer. How many of each? I don't know. I made the test last week. So I would not ask you PF6 minus. That would be a grade 12 one, but it would require knowing something about the atomic structure of the atom. So no, the test will have has some multiple choice. I don't remember how many, and then it will have a series of short answers. How many pages? I don't know. It has a legend. It has chapters, verses. Listen, I could give you a test with one question. And if that one question took you all class to do it, then that one question will be super hard. Or I could give you a test with lots of simpler questions, and you have to work through each of them. And what that does is if you don't know one topic, it helps to alleviate the penalty of that one topic. And you have to work through it, right? And so the number of questions makes it that if you don't know one topic, then the penalty of not knowing that one topic isn't as great. I'm not sure if the chemistry test has a Bible. As I said, we should bow down to the great and all-knowing periodic table, but Bible, well, that might be going a bit far. On a scale of 1 to 10, how hard do I think this test will be for you? To be honest, a 9. It's a challenging material. It's a challenging topic. The easiest I could make this test if I tried to make it super easy for you is an 8 because of the material. Now, what I will say, though, is that if you've done the work, and if you've been working all since September till now, and every time we've had a topic, you've done the homework, you've asked questions, and you've participated in class like many of you who are in this chat have done, then getting a test that has a level difficulty of 9 is not outside of your ability. It means that you're going to have to be methodical about how you answer it. You have to, when you get a question, pause, read the question, and answer what you know about it. But the number one thing that you're going to have to do is you're going to have to manage your time, because that is a big thing that students say about my tests, is that they find them long. So therefore, you have to manage your time. So you have to look at the material and work through each question. Just like in any other class, the number of marks on a question tells you approximately how many marks how many minutes you should spend on that question. Everything that is on a test, you have seen in class. You'll notice that I haven't given you textbooks, because the textbooks are just extra information that can confuse you. Okay? Everything on the test, you have either been given in a note, or you've copied in a note, or you've been told to make a note on yourself. Plus, we have answered questions like it on the test. So in the class. So there is no question that is outside of what we have done. Everything on the test we have done in class. So if you study your notes, and if you've done your work all along, you are fine, whether it be a level 1 or a level 10. So you will get the entire period. Okay. So the one thing is that you'll have to do is when you come in the room just before O Canada, you have to make sure we set up the cheat busters. And then O Canada will start. And then right after O Canada, I'll pass out the tests. Okay, now hearing some of you talk about stress and accusing each other of stressing out more or less than others, I am going to have to remind you, don't focus on the mark. If that's your focus, you will fail, no matter what. If you are focused on just the mark, then you're never going to be happy with the mark you get. You focus on the learning. And if you focus on the learning, you'll get a mark that you will accept because you will know that you have learned something. I can't promise that I'll be available before the test because I'll be in a gym with a practice for basketball. But I should be in the room a couple minutes beforehand. Okay, so the prefix thio. Okay, so for example, we see it, for example, in thiocyanate. What the prefix thio tells us is that we've replaced an oxygen in my oxyion with a sulfur. So for example, cyanate is, oh, I wrote it backwards, OCN minus. Okay, so this is my cyanate. If I take this oxygen and I replace it with a sulfur, because I've replaced an oxygen with a sulfur, they'll form similar bonds since they're in the same group. It's a thiocyanate. And so it only occurs with sulfur. Okay? And so I can do it with any oxyion. So if I wanted to do it, for example, with my phosphate, right? If I wanted to take one of these oxygens and replace it with a sulfur, then this would be a thiophosphate. As a thio tells me that the sulfur, one sulfur replaced an oxygen. So we know that our compressed octet will be boron, beryllium, potentially aluminum, and potentially magnesium. And I say potentially for these two because depending on what they're bonded to, they may have more of magnesium, and aluminum may have more of an ionic bond. Okay. Sorry, I keep forgetting pencil doesn't show up. So depending what these two are for, they're more likely to align to ionic because their electronegativities are so small. But if they're bonded with something that allows for an electronegativity difference that is less than 1.7, then they'll have a compressed octet. Boron and beryllium, they have a compressed octet of 6. Boron and aluminum. Beryllium and magnesium, they have a compressed octet of 4. And they always will be compressed. They'll always be less than 8. If we, in grade 11, we're limiting it to just these two, if I want to know if these two are expanded or not, Well, I have to look at the number of bonds. And so because it's bonded with 3 chlorines, and chlorine can only form 1 bond, I need 3 bonds. Phosphorus can be 3 bonds without being expanded. Whereas if I'm like this, I now have 5 chlorines and I need at least 5 bonds so that each one of them can be bonded to the phosphorus. I have to be expanded. Okay. And the same thing goes with the sulfur, right? So if I had, for example, SF2, I need 2 bonds, one for each fluorine, for it to be able to bond to the sulfur. Sulfur, since it can form 2 bonds not being expanded, it's not expanded. Whereas here, now I need at least 6 bonds, so each fluorine can bond to a sulfur. It has to be expanded. So I have to look at what it's bonding to. What do you mean, how would I draw it, Hadessa? I won't ask you for Lewis structure of something with more than 4 bonds on it. 4 bonding groups. Right? Because, for example, in my phosphate, even though it's an expanded octet, and my phosphorus has 10 electrons around it, right? I still have only 1, 2, 3, 4 electron groups. And so as a result, it's an AX4. And so 4 electron groups. That's the maximum that you need in grade 11. I won't ask you to define a thing. You just have to be able to use the terminology of chemistry properly. So just how we've been using the terms in class. Electron dot is Lewis structure, yes. Oh. Humaira, we would look at the attractions between that a compound can form to determine its melting point or boiling point. Remember, we sort of rank them, right? If we wanted to go from high to low, if this was my melting point, and this is our boiling point, then if we looked at our degree of attraction, this would be a high attraction between the particles and a low attraction. So now we said something with a low attraction probably will only have London dispersion forces. But if it's really big, it could be higher. Something with really high, it'll be ionic with electrostatic attractions. Or it could have all 3 of our intermolecular forces, right? Something that we would classify in the middle would probably have only a few intermolecular forces. And so the degree of attraction would tell us. And so high melting point, our highest melting point and boiling point will be ionic. And then after that would be a polar compound that can form hydrogen bonds. Then after that would be a polar compound that can't form hydrogen bonds. And then we'd have a non-polar compound. And that would be sort of how I would rank them. Now, if I have a really big nonpolar compound, it could bump it higher than a smaller compound that has these, but that's for later in the year. I won't ask you to say if it's high, low, or medium. I'll ask you to compare the melting point to things. And so it'll be which one is higher, which one is lower. Yes, you get the electronegativities of all the elements that you need it for. You get the chart that you got. So it has the AXE formula. It has the name of the shape, and it has a diagram. And so the diagram, remember, might be something like this, where you have to remember, don't put the dots. I want the actual symbols, right? And so you would replace the dots with the symbols of the elements. So you get all of that. You get the AXE formula, the shape name, your diagram. You also get all of your electronegativities. And if you get stuck for the grade 11s, you will have the nice, lovely molecule still hanging in the room. They'll come down sometime next week for the grade 12 test. Okay, so it's 9:24. Take the next hour to go over your notes one last time. Take a deep breath. Make sure you get a good night's sleep. Don't be staying up all night studying, because then you'll be tired and you'll make stupid mistakes on the test. Okay? The test is written to the period, so it should take you the entire period to do. Okay? Yes, that is true. If it's symmetrical, it will be nonpolar. Okay, so make sure you get a good night's sleep. Make sure that you're in well rested, that you get to school on time. Okay. Okay, so the recording will be in the link for it will be in the classroom once YouTube is done processing it. So have a good night, everyone.